Hello, students. At this point, we have quite a bit of experience finding the zeros of polynomials, and we've looked at a few examples where we found complex zeros of polynomials, and you may have seen a pattern. In the examples that we've seen before, in one example, 1 plus I and 1 minus I were the zeros of a polynomial. And in another example, -2 plus root 2i and -2 minus root 2i were zeros of another polynomial. And these pairs of numbers, there's a special relationship and a special name. We actually call these complex conjugates. And I'm actually going to write this out. So two numbers of the form a plus bi and a minus bi are called complex conjugates. And we can see here that these pairs of numbers are complex conjugates. Basically, they're the sum and difference of the same real and imaginary parts. So we've got 1 plus I and 1 minus I, and then we've got -2 plus root 2i and -2 minus root 2i. And in general, when we're looking at polynomials with real coefficients, if we have one complex number as a zero, we're also going to have its conjugate as a zero. And this is called the conjugate zeros theorem. If the polynomial p has real coefficients, and if the complex number z is a zero of p, then its complex conjugate, z with a bar written over it, is also a zero of p. This is a way that we write complex conjugates. So I want to go through just one example and show you how this works. So in this example, we will find a polynomial of degree 3 with integer coefficients and zeros given by 2 and 3 minus I. So because we have integer coefficients, that means that we have real coefficients because all integers are real numbers. And so since 3 minus I is a 0, that tells us that its conjugate, 3 plus I, is also going to be a zero of the polynomial. So when we know the zeros of a polynomial, we can then express the factors and use that to figure out what the polynomial is going to be. So our polynomial is going to be x minus 2, since 2 is a 0, times x minus 3 minus I, since 3 minus I is a 0, times x minus 3 plus I, since 3 plus I is also a 0. Now, we can actually simplify the second and third of these factors if we distribute the subtractions. This gives us x minus 3 plus I times x minus 3 minus I. And there's an interesting thing that's going on right here. In the second and third factors, we have a sum of two terms times the difference of those same two terms. And we know from our special product rules that that is actually the difference of two squares. So keeping the x minus 2 out front, we know that we can rewrite this product as x minus 3 squared minus I squared. Now this gives us x minus 2 times x squared minus 6x plus 9. And remember that I squared is negative 1. So if we're subtracting negative 1, it's the same as adding 1. And so this gives us x minus 2 times x squared minus 6x plus 10. And if we want to figure out what this product is, we can use the table method. We've got x and negative 2 on the left, and then up top we've got x squared, negative 6x, and 10. Multiplying out gives us x cubed minus 6x squared, positive 10x, negative 2x squared, positive 12x, and negative 20. And when we combine like terms, this leaves us with x cubed minus 8x squared plus 22x minus 20. And this is our third degree polynomial with integer coefficients and the zeros we were asked to have. One last note: if you struggled to see that this was a sum and difference that gave us a difference of squares, the alternate way to figure out what this product is, because we have 3 terms times 3 terms, is to use the table method with a 3 by 3 table. We've got x, negative 3, and I, x, negative 3, and negative I. And when you fill everything out, which will take just a moment, negative xi, positive 3i, and negative I squared, we can see that the 3i and negative 3i cancel. The ix and negative ix cancel, and so we get x squared minus 6x plus 9 minus I squared, and so that's the same as we have over here, x squared minus 6x plus 9, and that minus I squared becomes a plus 1, and we get the same answer in the long run. But doing it this way actually gives you an idea of why the conjugate zeros theorem is true. If we have one complex zero and we also have its conjugate, then when we multiply them out, this is going to give us a sum and a difference with the i's on the outside. That's going to turn into a difference of squares, and the imaginary part is going to get squared, which turns it into a real number. So through this example, we can get a glimpse of why the conjugate zeros theorem is true.